Greetings, calculus friend. I wanted to spend a bit more time with you today talking about the formal definition of a limit. In particular, I want to talk about a situation or a function where the limit doesn't exist. The limit doesn't exist. I want to first review the formal definition for a limit. The formal definition of the limit is the thing that we have to see whether it's true or not in order to write that the limit as x approaches a of f of x equals L. I get to write this and know that it's true because I can just write any sort of nonsensical things down. I get to write this down and know it's true if no matter the epsilon, no matter the distance, no matter the epsilon, you can always find a delta. And that delta guarantees that if the distance between x and a is less than delta, then the distance between f of x and L is less than epsilon. So no matter how small someone says epsilon is, you can always find a delta that guarantees that the function values are small if the input values are sufficiently close. I have drawn a piecewise defined function. It's got two branches, a left branch to the left of one and a right branch to the right of one. You know what? I'm going to make those two so there's not as many ones floating around. Okay, so we should draw a picture of this function. Axes. X. The left branch. 2. The split point. So it's going to jump. It's open. It's going to jump to x plus 1 with a closed circle right here. So this is x plus 1 and x. And I am naturally going to consider, as far as this problem, the limit as x approaches 2, because that's the interesting place. So I would like to think about the limit as x approaches 2 of f of x. This height here is 2. This height here is 3. So if the limit is some number, if the limit of this function is some number, which it's not because the two different sides are different from each other, the one-sided limits differ, they're not equal, so the limit doesn't exist. The two-sided limit doesn't exist. So what goes wrong? Well, I should be able to, if this is true, I should be able to, no matter the epsilon, find a delta so that I have to be no further away. I can be no further away than delta down here, and it guarantees I'm inside of epsilon over here. So let's put a delta window around, let's say, split the difference, and call that 2.5. No, there's no value I can choose that is the limit. Okay, so I'm going to let epsilon be 0.25. So I can go as far up as 2.75 and as far down as 2.25. Okay, so the question that we're going to ask now, so it says for all, here is an epsilon. Can you find a delta so that if the distance between x and 2 is less than delta, then the distance between f of x and, let's see, 2.5 is less than 0.25. L is, I'm proposing that the limit is 2.5. It's a lie. It's not, because this definition fails. Right? So here's L. This is the epsilon greater than 0, the arbitrary thing. Here's our point of focus. Can I find the delta? Can I find the delta? I would like to argue graphically that the answer is no. Okay? The answer is no, because if epsilon is 0.25, from the left, the closest you can get is a height of 2. The closest you can get is a height of 2. From the right, the closest you can get is a height of 3. No matter what, the absolute value of f of x minus 2.5 is at least 0.5. So that's because the vertical distance, the closest I can get here, the closest you can get, is a half a unit away. You can't make it be smaller than a quarter because the closest you can get is a half. There is no delta, no matter how close you get here. No matter how close you get on either side of 2 as an input, you can't get inside of this window. Let me adjust my picture a little bit. So our window that we're interested in, and we should be able to make this as small as we want, is this. Here's my window. And no matter how small I make this window, I chose a problematic one, no matter how small I make it, I can't, no matter how small I make this, I can't make this tight enough. No matter how small I make this, I can't end up inside this window here. These function values always lie outside of the shaded gap right here. If 2.5 were the limit, then I'd be able to say, oh, well, you just have to be this close. But no matter how close you get to 2, you're always outside of this gap here, outside of what I think of as the window, this shaded band. So since there are bad bands, since there are bad epsilons, there are bad widths of this. Since there are bad widths of this, the limit is not equal to 2.5. So to answer your question, to answer my question that I'm posing to you, can I find a delta greater than 0 so that if the distance between x and 2 is small, then the distance between f of x and its limit is as small as we want it to be? The answer is no. There are bad epsilons. Okay. There are bad epsilon values. Right? All you have to do is shrink the window sufficiently, and then you can't get close enough. You can't get close enough. And that's why the limit as x approaches 2 of f of x is not equal to 2.5. Nor is it 2, nor is it 3, nor is it any value in between, nor is it any other value at all. Right? No matter what number I put right here, this process is going to fail if you just make epsilon be small enough. That is to say that the limit doesn't exist. So I want to say thanks for watching and considering epsilons and deltas today. And I wish you all the best. Thank you.